This is section 2.4 on the precise definition of a limit. Okay, so on page 106, here's a precise definition. So what do you want to put on your formula sheet? Perhaps is everything here. The limit as x approaches a of f of x equals L means for every epsilon, this is epsilon greater than 0, there is a delta greater than 0, such that if 0 is less than absolute value of x minus a is less than delta, which means x is close to a, then absolute value of f of x minus L is less than epsilon, which means y, which is f of x, is close to L. Okay, so here's the format of it. So some background. Okay, so 2.4, this is the Greek letter delta. It's a lowercase. There's also a triangle for delta, but lowercase delta. It stands for a small change in x. Like you've heard of delta x before, but now we're using it in a different sense. Epsilon is a small change in y. So here's a delta, here's an epsilon. Okay, here I'm asking what's the difference between a and x? Well, you would take bigger minus smaller, x minus a. Suppose the picture looked like this on a number line. Here's a, here's x. What's the distance? A minus x. Okay, but what if you don't have a number line? You just want to say, I want the distance between x and a. You don't know which is the larger. So to make it a positive quantity, take the absolute value of x minus a. So that's the distance between x and a. Okay. Similarly, the distance between f of x and L is absolute value of f of x minus L. Distance between x and a is smaller than delta. Absolute value of x minus a is less than delta. Distance between x and a is smaller than delta, but not 0. Then I put a 0 in front. 0 less than absolute value of x minus a is less than delta. Okay, and the distance between f of x and L is less than epsilon. That's absolute value of f of x minus L is less than epsilon. Okay, so that's the motivation behind everything that we see here. Okay, so this means distance between x and a is small. X is close to a, but it's not 0. Here, f of x and L, or y and L, are close to each other. This time we are allowing for the possibility of the distance being 0. That's allowed for y, but not for x. That's less than epsilon. Okay, so what does that mean now for the homework? So 2.4, 1 to 4 all, 13, 15 to 20. The highest was 27. So let me show you that. Okay, so it's on page 113. So here it is for those of you who don't have the book and aren't getting it. That's 1 through 4, and we don't have anything up until 13. So go to the next page. There is 13, and we had to go as high as 27, I believe it was. So there we go. Okay. All right, so 1 through 4 all. So let's take a look at number 2. So use a given graph of f to find a number delta such that if 0 is less than absolute value of x minus 3 is less than delta, then absolute value of f of x minus 2 is less than 0.5. So the limit is supposed to be 2. I go 0.5 in the y direction, up and down, 1.5, 2.5. This corresponds to 2.6 and 3.8. So the delta that I pick is the smaller of the distance between 3 and 2.6, and the distance between 3 and 3.8. So the smaller number is 0.4. That's my delta. So in other words, if I go 0.4 to the left and to the right, then all the y values are going to be within 0.5 of 2. You don't want to pick the larger number. So if I pick 0.8, well, this side 0.8 would lead me to 2.2. 2.2 would send me outside of the region where epsilon is within half a unit of 2. Okay. All right, and then number 4. Here's a graph of y equals x squared. Find a number delta. All right, so they went 0.5 and 1.5. So I want the y coordinate to be 0.5. So I plug in 0.5 equals x squared, take the square root, 0.707. Similarly, what's the x coordinate if the y coordinate is 1.5? Plug in 1.5 for y, take the square root, 1.225. Okay, so the distance between 1 and 0.707 is 0.293. Distance between 1 and 1.225 is 0.225. The delta should be the smaller number, which is 0.225. Okay, so that's what we have over here. Okay. Now, how do I do all the rest of the problems, which are basically proofs? Okay. Prove all of these using epsilon and delta. And I'll show you how to do that now. Okay, first 13. Absolute value of x minus 2 is less than delta. Then absolute value of 4x minus 8 is less than 0.1. Okay, this is basically a setup to say that the limit as x approaches 2 of 4x equals 8. It's obvious by direct substitution. But when we set up these problems, this is f of x and L. So absolute value of f of x minus L is absolute value of 4x minus 8. And x approaches 2, that's where we say x minus a, x minus 2, and absolute value is less than delta. Ordinarily, we would put a 0 on this side. They don't give that to us. Okay, so all I do is I force this to look like this. In other words, from here, factor out the 4, divide both sides by 4. I have absolute value of x minus 2 is less than 0.025. And now that matches this, x minus 2, x minus 2. So that delta equals 0.025. Okay, so I use this arrow for implication. You should do likewise. Absolute value of x minus 2 is less than delta implies absolute value of x minus 2 is less than 0.025. Multiply both sides by 4. So absolute value of 4x minus 8 is less than 0.1. That is considered the end of the proof. Okay, so whenever delta, if epsilon is less than 0.1, okay, then the delta being 0.025, I have satisfied the requirement that whenever this is true, then this is true. Okay, so how do I do all the other kind of proofs now? Like 16, limit x approaches 4 of 2x minus 5 equals 3. So this is my A, this is my f of x, this is my L. So I'm basically trying to get everything to look like this. This limit x approaches A, f of x equals L. So I need my f of x and L. That's going to go in absolute value here, less than epsilon. And I'm going to have x minus A, that's going to be over here. Okay. Let's see how to do that. So what are we trying to do? This is my A, f of x, this is L. So given epsilon greater than 0, find a delta greater than 0 such that this language will always be there. So you should put this language in every problem in this section. Okay. So 0 less than absolute value of x minus A, in this case it's x minus 4, is less than delta, implies, arrow means implies, absolute value of f of x minus L, is 2x minus 5 minus 3, is less than epsilon. Okay, so first we do scratch work, quote unquote. I start off with this, absolute value of 2x minus 5 minus 3 is less than epsilon. I try to force the left-hand side to look like x minus 4. Usually the calculation is not too hard. So that becomes, implies absolute value of 2x minus 8 is less than epsilon. Factor out the 2. 2 absolute value of x minus 4 is less than epsilon. Divide both sides by 2. Absolute value of x minus 4 is less than epsilon over 2. So that now matches that. So all I do is set that equal to that. In other words, let delta equal epsilon over 2. Okay? So if you give me an epsilon, here's the delta that I picked. So if you give me epsilon is 0.1, I'll divide it by 2 and I'll say delta is 0.05. If you give me epsilon is 0.002, I'll let delta be 0.001. Okay, now for the actual proof that this will always work. Start with 0 less than absolute value of x minus A, x minus 4, less than delta. I basically just retrace my steps. Multiply both sides by 2. So absolute value of x minus 4 is less than epsilon over 2, because that's my delta. Multiply both sides by 2, and I get absolute value of 2x minus 8 is less than epsilon. Final step is to force this to look exactly like that. I know ordinarily you would never make that step in algebra 1. I mean, we would normally go from here to here, but just because of the rules of the game, I have to write it as f of x minus L. You change that, to this, which is clearly true, right? So I just write absolute value of 2x minus 5 minus 3 is less than epsilon. 2 lines means end of proof. You don't actually have to put the 2 lines, but that does show that we're finished with this problem. Okay, here's 17. Limit as x approaches negative 3 of 1 minus 4x equals 13. Here's my a, here's f of x, here's L. So we always start with the same language, given epsilon greater than 0, find a delta greater than 0, such that 0 less than absolute value of x minus a, x minus a minus 3, less than delta, implies absolute value of f of x, 1 minus 4x, minus L 13, less than epsilon. Okay, so the first is scratch work. I start with this, 1 minus 4x minus 13 is less than epsilon. Try to force the left side to look like that. Okay, so that gives me negative 4x minus 12 inside the absolute value. I can factor out the negative 4. Negative 4 parentheses x plus 3 is less than epsilon. Take out the negative 4, becomes a positive 4. Positive 4 parentheses x plus 3 is less than epsilon. Divide both sides by 4. And I have x plus 3, which is x minus a negative 3, is less than epsilon over 4. Okay, so I got that to match that. So now I say delta equals epsilon over 4. Okay, this is all scratch work to show that delta is epsilon over 4. Now for the formal proof. 0 less than absolute value of x minus a, x minus a minus 3 is less than delta, means absolute value of x plus 3 is less than epsilon over 4. Usually when you get to this stage, you can ignore the 0. Just drop the 0. Okay, multiply both sides by 4. 4 absolute value of x plus 3 is less than epsilon. Distribute the 4 back in and make it a negative 4, which is required. You're just sort of retracing your steps back here. Absolute value of negative 4, x plus 3 is less than epsilon. Granted, in algebra, you would normally never make this step, but we have to by the rules of the game to actually show the proof. Distribute, and then just rewrite it the way that I want to, which is absolute 1 minus 4x minus 13 less than epsilon. Okay, I mean, if this is true, this is certainly true. I mean, if you work this out, that is negative 4x minus 12, although normally you would never make that step, but here it's required by the rules of the game, so to speak. Okay, so that's that one. Do a few more. Here's 2.4, number 19. Limit as x approaches 1 of 2 plus 4x divided by 3 equals 2. This one's a little harder because of the fraction. By the way, you want to check to see if it's believable. Okay, if I plug in 1, I get 2 plus 4 is 6 divided by 3 is 2. It's believable. Okay, so write all this stuff. 0 less than absolute value of x minus a, x minus 1 less than delta, implies absolute f of x, 2 plus 4x over 3 minus 2 is less than epsilon. Okay, so scratch work, so to speak. Start off with this. I put that, get a common denominator, 2 plus 4x over 3 minus 6 over 3. Combine, giving me 4x minus 4. Factor out the 4. 4 times x minus 1 over 3. And I want just the x minus 1. So I factor outside the 4/3. So 4/3 absolute x minus 1 is less than epsilon. How do I get rid of 4/3? Multiply both sides by 3/4. So absolute value of x minus 1 is less than 3/4 epsilon. And on this side, I now have absolute value of x minus 1. So I let delta be this. So let delta be 3/4 epsilon. Now for the actual proof. You sort of just retrace your steps. 0 less than absolute x minus 1 less than delta implies change delta to 3/4 epsilon. Multiply both sides by 4/3. 4/3 absolute x minus 1 is less than epsilon. Distribute the 4/3 back in. 4/3 x minus 1 in absolute value is less than epsilon. Distribute 4x minus 4 over 3. And then the next step, again, is a step you would normally never make in algebra, but if you're forced to retrace your steps by the rules of the game. So I go ahead and write it as 2 plus 4x over 3 minus 6 over 3. This is certainly a true statement, right? If you clean up that algebra, you get that. And then I have what I want. I have absolute value of f of x minus L is less than epsilon. So 2 plus 4x over 3 minus 2 in absolute value is less than epsilon in the proof. Okay, 23, limit as x approaches a of x equals a. This one's almost too easy. Okay, given epsilon greater than 0, find delta greater than 0 such that 0 less than absolute value of x minus a is less than delta, implies absolute value of f of x minus L. So the f of x is x and the limit was a is less than epsilon. Okay, so I need this to look like this, but it already looks like that. there's no algebra to do. Just let delta be epsilon. So 0 less than absolute value of x minus a is less than delta. Well, since delta equals epsilon, then I already have absolute value of x minus a, which is also, in this particular case, absolute value of f of x minus l is less than epsilon. So that's it, end of proof. 24 is kind of trivial also. Limit as x approaches a of c equals c is a constant function. That's my f of x, that's my l. So given epsilon greater than 0, write all this again. So 0 less than absolute value of x minus a is less than delta implies absolute value of f of x minus l is less than epsilon. Well, f of x is c, l is also c. So I have 0, absolute value of 0 is 0. So 0 is less than epsilon. That's already true, no matter what I pick for delta. So you can let delta be anything. So I pick delta equals 1, but you can let delta be 2, 3, 80, anything that you want. And that already shows that 0 less than absolute value of x minus a is less than 1 implies absolute value of f of x minus l, that's c minus c, which is 0. That's already less than epsilon. Okay, so it's kind of too easy here. Okay, and then 25 is what I wanted to show you. Limit as x approaches 0 of x squared equals 0. Here's my f of x, here's my l. So given epsilon greater than 0, find delta greater than 0 such that 0 less than absolute value of x minus a, that's x minus 0. I like x minus 0, that's just x. Implies absolute value of f of x minus l, that's absolute value of x squared minus 0, is less than epsilon. Okay, so scratch paper, absolute value of x squared minus 0, less than epsilon. That means x squared is less than epsilon. Take the square root of both sides. I have absolute value of x is less than epsilon, and that is the left-hand side. So let delta equal square root of epsilon. So retrace our steps. 0 less than absolute value of x minus 0 less than delta. Change this to absolute value of x is less than delta is equal to square root of epsilon. Square both sides, so that implies absolute value of x squared minus 0 is less than epsilon, which is what we were trying to prove. Okay, that's pretty much about it. The last one I wanted to show you was 27 as a hint. They're trying to say 27, limit as x approaches 0 of absolute value of x equals 0. Okay, so if you do it the right way, you have an absolute value inside an absolute value. Okay, so we know like absolute value of -5 is 5, absolute value of 5 is 5. But what if you have an absolute value inside an absolute value? Well, it's actually redundant because by order of operations, if I do the inside absolute value, I have 5, right? So that's 5, and now the absolute value of 5 is 5. So if you have double bars, you can basically drop it. In other words, absolute value of x is the same thing as the absolute value of x. So that's a hint for problem 27. All right, so that was section 2.4.